right, I guess we should get started. So welcome back, everybody. Happy New Year. Um, Welcome to the first 2026 edition of the RFMIG, and it's a great pleasure to have Li-yao, who is going to be talking about all the work that's been going on in Creusot over the past, I guess, 2 years at this point, since I handed off the project. Um, and I'm very excited to see everything that they've been cooking up. So take it away.
Thank you. Yeah, this is a joint work with the rest of the Creusot team at LMF. I think most of us here are already aware of what Creusot does, but just to give some context for those who might not, is that Creusot is a deductive verification tool. That means that the goal is to verify that a program satisfies its specification. And in particular, that means that means that the program is not going to panic or have any kind of undefined behavior. So here's a simple example of a Rust program that takes a Boolean and two borrows and returns one of the two borrows uh, based on the Boolean. And so what we can do then is to first give a specification of this program um, in terms of a contract, that is pre and post conditions. So for this simple function, there is no precondition, so it can take any Boolean and any two mutable borrows. And the post condition is that the borrow the return borrow must be either X or Y, depending on the value of B, and the other borrow must not have been modified. And so one of the things that this example demonstrates is also the prophetic model of mutable references at the heart of Creusot. What this means is that mutable borrows are represented as a pair of two values. The initial value that we write using the dereference operator, and the final value that is the value when the of the borrow when the borrow ends. That is what we call the prophecy for this borrow. So one of the subtleties here is that the choose function itself doesn't mutate X or Y, but it's the caller of choose which is going to make use of this mutable borrow and write to it. And the final value when the caller lets the lifetime of the borrow ends is going to be what this caret y or caret x value is going uh, to be. So just to make the things a bit more concrete, I've prepared a small demo. So here is our example again. And so what we can first do is compile this program. So this is what you do with this cargo Creusot command. And so the result of that is that you obtain some comma file that correspond to this function. So comma, and so you essentially get a lot of code in some uh, specialized verification language, and then we can use we can run provers on top of this program using the cargo Creusot prove. So this says that, well, we have managed to verify that this function satisfies its contract. So one thing to make things a bit more interesting, we can try to make the contract, write a wrong contract by maybe confusing X and Y. And so in this case, we find that, well, the contract doesn't prove. And we can also use, in this case, maybe we want to troubleshoot to figure out what went wrong. And so what you can do is restart the Y3 IDE, which is a graphical environment for inspecting the proof status of some Y3 codes. So here we can see the various goals that have been generated for the choose function. And so we see that, for example, here there is a goal that hasn't been proved. And so when I clicked on it, I had a tab into the Rust file that highlights the parts that this goal corresponds to. So of course, this comes from trying to prove the post condition of the function. And then in the task window, we can see a bit precise, uh, more precisely the formula that we are trying to prove here, which is corresponds indeed to the x equals y uh, that is wrong. All right, so I'm going to just fix it again. And so we can also, oops, and then we can move it. All right, let's go back to the presentation. So, to give in a more graphical way what we've just seen. So as an input, we take a Rust program and a specification. And so Creusot is this big box that in the end outputs whether you've managed to prove the program satisfies the specification or it has not, and then you have to figure out what's wrong. And so inside this box, the first step is to compile this Rust program.
Li-yao,
Yes?
sorry to interrupt. I just only noticed that some people ask questions in the chat. Bart and Julian, are your questions still relevant?
I'm happy to be interrupted if you have questions.
Well, it's not actually. Well, let's ignore it. It's not important.
Okay.
Sorry.
All right, then. Sorry. I guess next time you feel like you have an urgent question, I guess just speak up.
Yeah. All right.
All right.
Sorry. Continue.
But yeah, I'm happy to be interrupted at any point if you have questions. So the first step is to compile the Rust program to this intermediate verification language named Comma. And Comma is an input to the Y3 platform, and which is going to take this Comma program and generate proof obligations for this program that can then be dispatched to many SMT solvers. So one of the strengths of Creusot is that we inherit from Y3 is that we can leverage many many SMT solvers which have their own strengths and weaknesses. Right. So this is not the first time that Creusot has appeared in the Rust formal methods groups. So to give a bit of history, before Creusot, there was this Rust form project which presented the prophecies model that Creusot depends on. 1 year later, there was this Rust on belt which combined the prophecies model and the Rust belt project that formalizes the semantics of Rust. And soon after, that's where Creusot came, and that's its first presentation at Rust formal method groups. Creusot has been used in a verified SAT solver by Sorek. Another presentation of was the addition of type invariants by Dominique. And this year, just 2 weeks ago, we had a presentation by Arnaud at CPP of ghost permissions, which I will talk about in this talk too. I presented a tutorial also at Popo, and now we are here. So ghost permissions is kind of the big feature that we've been that has been added last year to Creusot, and we've been looking for many case studies to do it. So what is the problem that it's trying to solve? So so one thing that Creusot already deals with well is references. So here is a small example program that takes a mutable reference and then a shared reference y. And what this program guarantees is that the mutable reference X does not alias the shared reference Y, and so we can deduce that when we write to X, the result of Y is not going to change. So we can write a simple specification for this function. On the other hand, when we try to use row pointer, a more low-level feature of Creusot, of Rust, we can try to write the same function. And here we find that it's actually not even obvious how we can write the specification of this function. The problem is that in a way, this function just takes like 2 pointers, but there is no real way in Creusot to refer to what X and Y point to. Moreover, we probably want to reason about aliasing to, well, say that X and Y don't alias if we want to try to reproduce the example on the left. But also, we might also want to use this function with X and Y that are indeed aliased and verify this kind of example where we take an X and we create a pointer and we pass the same pointer to both as both arguments. And this is in fact safe to do, and you get the result 42. And so the solution we came up with, well, inspired by Verus, is the notion of using ghost permissions. So in a way, we can think about row pointers in comparison with references, as in we have these different types of references are as a kind of checked pointers that have that are checked by the Rust borrow checker. And so the difference then is that row pointers lose track of the information of who owns this data. And so between the safe references and the row pointers, we have unsafe casts, and that's where we are going to change in order to get a more a way to reason about pointers. So what we do is we add a type of type we call of permissions that represents the ownership of the pointee as a form of ghost data. What this means is that this permission type is going to be borrow checked, but it's going to be erased at runtime. And so what we do is just add this permission as along with the pointer. And so in that case, we actually can define the casts as functions between these two types. And in fact, they are going to be inverse functions. And so while these functions are still unsafe, they can be verified. That is that these functions that cast between safe references and row pointers plus permissions have safety conditions expressed in their contracts so that you can use Creusot to prove these safety conditions, and so that your program does not have undefined behavior. So there are quite a few applications that we've worked on using ghost permissions. So one of the first one was to use to reason about interior mutability, notably the cell type in Rust. Another thing that linked list allow is the representation of linked lists, which is part of the Creusot tutorial that you can find online. Union find and persistent arrays are also two algorithms that make use of ghost permissions that have been presented by Arnaud at CPP 2 weeks ago. We also have an example using concurrency, and that's part of ongoing work. And finally, the example that I'm going to talk about today is using ghost permissions to verify the slice functions. So this problem is a problem posed by the verify-rust standard library challenge. And so it consists of 10 unsafe slice functions So the goal for them is to write a contract, and more specifically the preconditions that callers must satisfy, and then prove that these preconditions prevent undefined behavior. Furthermore, there are also 27 safe functions that we want to verify. And so then the goal is simply to prove that there is no undefined behavior for these functions. And so I have my attempt at this repository, and that I can click on. And I've made a little table of the current status. So these of the unsafe functions, there are 7 that have been proved and 3 left. And here there are 6 safe functions that I have verified in a certain sense. All right, so. And so what I'm going to present today is, well, there's going to be a few theoretical questions, but really it's really a lot of engineering problems that we will see. And moreover, in fact, I didn't just prove the lack of undefined behavior, but I actually give complete functional specifications for all of these functions, which turns out to be not much more work than just proving safety, in my opinion. So here's an example of the this is the original function, an original function from the core library. So the split at function that takes a slice and an index and splits it into 2 sub slices. And so it uses this from row parts mut, which reconstructs a mutable borrow from a row pointer together with its length. And moreover, there is the add function, which has a non-trivial safety condition, which is that the range between pointer and pointer plus mid must be in bounds of the slice. And we will see soon why it turns out to be a bit of a tricky condition to verify this. So to verify this function, we want, I'm going to start to make it as close as possible as the code above. So what we do is that we want to make these permissions that I mentioned earlier explicit. So the permission is going to come from casting this mutable borrow self into a row pointer. And so we replace the cast that's performed by this asmut pointer function with a wrapper that also returns the permission along with the pointer. The permission represents, in a way, what the contents of the whole slice. And so we will then want to use this permission to reconstruct the 2 subslices. So we first split this permission at the index mid, and to get 2 subs permissions. And then we use these permissions to reconstruct the mutable reference using this, again, verified wrapper on top of verified version of the from row parts. But there's still one hole left here, where when we add pointer and the index, we have to check that the range between pointer and pointer mid is indeed an existing slice. However, the evidence for this is contained currently in perm 0 or perm, which come from the first part of the slice we have already used to construct the first mutable borrow. And so for this, we need to, before we can use, pass perm 0 to the first from row parts, we must extract some liveness evidence that we use with this live mut method. So we take perm and we extract the liveness method before splitting it. And then we can use this liveness evidence to check that the addition pointer offset is valid. Any questions so far?
So I have a question. What part of this is checked by the Rust type checker or borrow checker, and what part is checked by Y3?
Right. So the part that's checked by the borrow checker is the ownership of perm. So here we have perm that's going to be a ghost mutable borrow of permission of a perm type. And so live mute and split are going to manipulate the lifetime of this perm, and so this is part of these lifetime are going to be checked by the borrow checker. And so then in the Creusot side, what we are going to prove is that when you use a permission, the permission indeed corresponds to the pointer that is actually part of the executable program.
Right.
Yep.
Is there like an API for this somewhere? I mean,
yes, of course.
Right.
It's on I can maybe just.
But it's not on the slides.
Yeah, it's not on the slides. I can just find it quickly. So here there's the API. Well, the Creusot version of the API, and it's in the let's see, pointer. It should be in the pointer version. I think it's this. Yeah, no, I don't remember exactly. And also, oh yeah, I can just go to the request that I have, for example. In this pull request where there are these facts, I think I have split somewhere here. Split, for example, which is let's see. So this is a split for the perm type, and so we have let's see. And for example, here what this says here is that word is really the accessing the pointer that is associated with the permission self. And so here we show that the pointer associated with self is the same as the pointer of the first component, and the pointer of the second component is going to be the pointer, an offset of this pointer and the index.
Right. So the model of these permissions is simply, as far as Y3 is concerned, is simply the pointer itself.
Right, the pointer and the value. So there are two fields, which is the word that the pointer and the value here that is contained in it.
Okay.
And so the value here is the slice itself. And then we have the at operator that takes the model of the slice, which is going to be a sequence of values.
Mm-hmm. Thank you.
Right.
And Sean also asked whether you model provenance.
So we don't explicitly model provenance. And yeah, it's implicit in the API. I think one way to think about it is that we don't model it, but for example, for example, it wouldn't be you won't be able to like cast a pointer to an integer and then back and then use it, because the cast from the point of view of well, Creusot is going to see that is going to just reject casting an integer to a pointer, I believe. We just don't have semantics for it. And instead, you would have to come up with some axiomatize some function that converts between the two and then give a specification for it. And in particular, this function, in a way, the way Creusot is going to see it is just going to be some opaque function that has some effect which would have to be well, coming up with the right provenance. All right. All right. So in order to do this verification, I've extended the API further on top of what we've already had for ghost permissions. So one thing we had to do to verify slices, of course, we had to add methods that give semantics to slice pointers. As we've just seen in the previous example, just having permissions themselves is not enough. We have to refine it into a separate kind of token that represents just the liveness of a slice without taking ownership of the permission itself. There are also some facts about size and alignment that were necessary to verify the slice functions. And finally, we also had intrinsics that make use of these permissions. So just to transition to the next part is looking back at this example. Well, this is above is the code from the core library, and below is the core code from the verified core library that I'm working on. And so I'm saying that this is basically a verified version of the function above. But the question then is, well, how can we actually be sure that's the case? And furthermore, since this is the goal of this is to eventually submit it to the as a solution for the verify-rust-std challenge, the question is is this going to be maintained? As for example, if someone wants to modify some slice methods, then how are we going to know if the proof is still up to date? So that's what the erasure check is going to address. So again, the goal is to ensure soundness, that is in the sense that the code we verified should match the code that we mean to run. And one might want to just run the verified code, but I think for now, it doesn't seem very likely that we are going to just have the Creusot ghost code into the Rust standard library. And then once we have ensured that the code matches, we want to find we can make use of this to help proof maintenance to make sure that the verified code and the original code still match. So the idea is, well, we start from this code to verify, and some Creusot expert is going to indeed verify this function by adding pre and post conditions and the necessary ghost code. And then we want to make sure that we have some automated check that the verified code matches the code to verify, in the sense that if you erase all of these ghost annotations, then you get back the original function. And then when the core library gets updated, then we run the erasure check, and maybe we find that the code no longer matches, then we can be notified and update the proof and make sure that the check succeeds. And this hopefully is going to be less work than doing the proof from scratch every time. So what this looks like concretely is a little annotation that relates the verified function on top of the verified function that just names the function that from the core library. And then they are going to match to compare the bodies of the two functions and check that they match up to ghost code. Another thing that's another feature that's necessary for this is that, well, the function we are going to verify are going to call, make use of functions that are not public in the core API. And so the erasure annotation supports going into the naming some private functions. And this turns out to be not very easy to do using the Rust API. So what we do is a hack, which is to reverse engineer the computation of the def IDs, identifiers in the Rust API. And somehow this works. So one more thing that making this erasure notion of erasure explicit in Creusot is that, well, sometimes ghost code can kind of seem like it requires to break your code a bit. So here's an example where from the so this is an auxiliary function that's used in reverse that takes mutable slice again and returns what this is a pair of two pointers, one to the beginning of the slice and one to the end of the slice. And so so it seems quite straightforward to do that. You cast self to a pointer, and that's the beginning of the slice, and then you add the length to that pointer, and that's the end of it. However, if you try to verify this code, you find that you have to do a bit of a change, and the resulting change is going to fail this erasure check because we have reordered the length, the call to the length function with the asmute pointer. And this is because when you try to add start and the length, previously you just called self.length, but now because we have made permissions explicit, when we the self is borrowed for the lifetime of a perm, and so we cannot refer to self anymore, and that's why we have to compute the length before before casting self to a pointer. And so the result is that, well, you have two functions that no longer match, and you have to argue that either we have to refactor the asmute pointer range function in core, or we have to make the erasure check a bit smarter by making it aware of a notion of purity. So that's, but yeah, I haven't gotten around to make a decision about that yet. Right. All right. So let's see. Yeah. So I have so we are reaching the end, and so there are a few more features that I want to talk to that haven't been implemented yet. So one is among the three remaining unsafe functions, there are two that involve some form of transmutation. So this align2 function takes a slice, and the idea is to transmute it into a slice from a slice of t to a slice of u, but t and u might have different alignments, and so you trim at the beginning and the end a bit to make the alignment work. I have there is also another function that's a special case of align2 that has been verified, which is the as_chunks function that takes a slice and returns a slice of fixed length arrays. And so to make this work, I have added the following axiom that takes a permission of a slice of t into a permission of the other of a slice of arrays, and there are of course preconditions that make sure that the length of this should be divisible by n, and then as a postcondition, it makes sure it tells you that the values here correspond indeed to the value of the original slice. And so the challenge here is to generalize that axiom into in some sense to a larger class of slice types, probably by defining some traits that the users can extend with valid transmutations between these slices. And another feature that turns out to be that is a bit surprising, to put it like this, is that actually Creusot does not prove safety. In fact, what Creusot currently focuses on is proofs of functional correctness. And what I mean is that, for example, if you write a function like this and you add a requires clause, what this proves is if P, then no undefined behavior happens. But what we really want is to prove that F is safe. That is, for any input, you cannot do any undefined behavior. And so in particular, this is regardless of what P is. So there is a bit of a mismatch between what we want for this challenge and what Creusot is currently doing. I don't think it's really that big of a mismatch, and that's why I've already put so much effort into verifying the function, even though what it verifies is not quite what is expected. And this check, I think, to give you an idea of what it would take to make this work, actually verifying the right thing. One thing we can note is that the safe functions have a very common shape, which is to just check the precondition and panic if it doesn't work. So I forgot to negate the precondition here. And otherwise called the unchecked version of the function. And so to verify that, we have to simply ignore the preconditions. And then when we check that the precondition is false, then we panic, and panics are safe. And finally, in the other branch, well, the precondition has been checked, so the call to the unchecked function should be valid. So it doesn't seem like very big change to make Creusot support this kind of use case. All right, to conclude, so I've presented a bit of how to use Creusot to verify the slice functions. So in total, there are 37 functions to verify, and I've verified about a third of it so far. All of this is made possible thanks to the support for ghost permissions for row pointers, and I've added some primitive for reasoning about slices. The erasure check is also important for actually answering the challenge and making it maintainable. So that is to separate the verified version, which is going to contain a lot of ghost code, separate from the actual core library, but have some mechanized connection between the two. And so as a future work, well, I want to make this erasure check more support traits and closures, which it doesn't deal with well at the moment. And so, as I mentioned before, there was these issues that sometimes it seems that we want to rewrite the function a bit to be compatible with the addition of ghost code. We also need some more detailed model of memory to be able to model transmute and also an initialized memory. And finally, there is this question of actually proving safety. And once we have done all of that, we can prove the rest of the slice functions. Thank you for listening.
Thanks for your talk. Mike, I have a question. And I guess the question would be, so you added a bunch of new like ghost types and ghost APIs and everything. Yes, Xavier, if you need to run, that's fine. So you added them, and I'm wondering, how do you know that the APIs or the like axioms you added are correct? Did you verify them? Do you plan to verify them? And yeah, I guess maybe that's the first part.
Right now, I would say I don't really have a very strong argument in favor. The main one is that I've been refining these axioms. Like this has been an open PR for almost a year. And we've plugged all kinds of holes that we found in the meantime. But so far, yeah, I don't really have an idea of. I mean, I think the ideal way would be to somehow formalize them in a formal model like Rust Belt. But yeah, this seems like very far in the future so far.
And then maybe also related, like I guess you maybe arguably you were just like trying to figure out how many axioms like are needed.
Mhm.
Do you think you've got them all now, and the remaining things can be solved with the existing axioms, or do you anticipate that one needs more?
I believe the issues with transmute and initialize memory are all of it, so that the rest of the function are like for like the last uh, unsafe function, for example, is indexing using disjoint indices simultaneously, and this is mainly a complex bit of reasoning, but doesn't really use any advanced axioms that I don't already have.
I see. Very nice. I also can use my power to prompt a question, because I feel like there might be some Verus people in the room. So I guess the question would be, how similar is what you're doing to the Verus approach of a linear ghost
Yeah.
types? I don't know. Maybe I don't know. I'm not sure if the
My
Verus people have
understanding
anything to
is
say
that
on this, but
Creusot's strength is in its handling of mutable borrows, that they are truly first class. And so what we can do is essentially combine this with the linear resources of Verus to do. So I think it's that essentially, for example, we return mutable borrows of permissions all over the place. And that relies on the fact that we can make them, yeah, that they are very first class in Creusot.
Florian, you have something to ask?
Yes, thanks. It was a really nice talk, and I'm really looking forward to learning more about the Erasure check. Um, but I have one question that goes a little bit beyond probably what this talk is about. Namely, do you think that it could be possible to not only get this Erasure check as something after you've written Ghost code, but maybe even have some reoccurring patterns as a heuristic, such that you take the actual standard library code and Creusot automatically inserts the handling of the ghost permissions for you and then verifies it? Do you think that's possible?
That's a very intriguing idea. Uh, I would say it doesn't seem completely that far-fetched. I think that's an interesting idea worth exploring.
Nice, thanks.
And Jono?
Yes, I'm curious about how the erasure check works. Could you elaborate a bit?
Yeah. Let me think a bit. So the way this so let me take the split mute example from before. Just so the idea is intuitively we erase the ghost, and the function below should match the function above. So for example, here we have these lets that are just ghosts. And so what we can, so first this works at the here level for now. Let me think, here, no, the here level. And so, which is reasonably close to the source level where these transformations can make sense intuitively. So when we encounter these ghost blocks, we erase them. There are one special case for this split function, which happens outside of a ghost block, but is morally a ghost function. So there are a couple functions like this that you have to erase. The other thing is, for example, matching here when we have functions that return ghost data alongside real data, then the way we do it is we always return them in a tuple, and then when you have a tuple of some real data and ghost data, well, you erase the ghost data and you try to match the patterns like this. And finally, when you have these functions that you have some wrapper that usually has some explicit permission, what happens is that this function is going to have its own erasure annotation, and so that lets you map this function to this original function as well. So yeah, it's a very syntactic check that that tries to erase ghost and see if what's left matches.
Thanks for the answer. Maybe related to this, so how often does it happen that there's no real difference in the code, but for example, you add something and then the Rust compiler lowers this in a slightly different way, and then the erasure check fails? Does this happen at all? Do you need to account for some very minor differences in places?
So that's I think when it works quite well. Let's see. So right now the main case where it did not work is the one I mentioned just below, where here between where sometimes. So I had one case where have this one case where I had to reorder some calls, and so this means this example is currently broken as far as the erasure check is concerned. I had another case is that is the use of the slice index trait for indexing into slices, and because what I've do is in my version of the code I redefine this trait so that I can extend like the methods with permissions. But then right now the erasure check is not able to take into account like relate these two traits, the traits in my version and the version of the core library. So that's another big feature that needs to be. And lastly, and the functions and the closures, local functions and closures are also a bit of a pain, because essentially every closure in a way has its own type. And so the closure in your version, in my version of the library, and the closures in the core version of the library don't match. And one would have to come up with some way of relating them too.
All right. That seems reasonable. And then also how, like you mentioned this like loop that you propose, where you have the Creusot ghost annotated version, and then you permanently check against the actual standard library. How often does it happen that like you need to change things there? I guess also how stable is the standard library?
That's a good question. Yeah, I'm not sure right now. I think I have seen some changes happen on the functions that intend to verify in the past year, but otherwise I don't really have much concrete I can say about it.
All right. Are there any other questions from other people? Okay, well, I guess it's the question about from, I'm not sure how to pronounce the name, OX, LLXO, whether you know that there's any SMT solver or something that people have built or are trying to build that uses Creusot, whether this would be feasible. I think someone mentioned the thing that Xavier once wrote. Now, unfortunately, Xavier had to leave, but well,
Yeah.
I don't know. Perhaps you know something about it.
No, I'm not aware of any work trying to go beyond what Creusot did.
Okay, fair.
But yeah, on the practical side, yeah, I guess I'm not very familiar with what goes into a SMPT solver to say something sane about it.
Yeah, me neither. I also have a question about slide 7, where you showed how you add the ghost permission everywhere.
Mm-hmm.
I guess is the perm type unsized? Why do we need to put it in a box?
Exactly, yeah, it's unsized. And in fact, originally it wasn't. And we found that this was unsound because I think it's from this version, the from mute, that takes a mutable borrow and turns it into a mutable borrow of a permission. And so what could happen if perm was sized is that you could just swap this permission with something else. And then when this function, you go, let's see, and so you get the permission elsewhere, and the mutable borrow is still like live, and so you get unsoundness this way by having a shared mutable reference.
I see. That makes sense. So does this crucially your whole encoding rely on the fact that you can't swap unsized things?
Indeed, yeah. So because what you would need in a way is that when you use the from mute method, the permission that in the end the caller is going to put back into this mutable borrow should be like the same one as the one that originated from it, but because of the prophecies model, it's not actually very easy to encode this requirement.
I see. Was that also what you had to add I think at one point somewhere in Creusot you wanted to add something like pointer identifiers. Was that for that?
No,
Or
for
like
the identifier
some
is
kind of extra
another issue.
metadata for okay. All right. Well,
For mutable borrows now they carry an ID, and that was because there wasn't soundness with the snapshot feature.
Okay. Well, I think this is at least I'm done with my questions. I had quite a few. Are there any other people that have more questions? You can also ask them in chat. Yeah, that's a fun one. How was the experience participating in the verify-rust-std competition?
I would say it has been mixed. I did not expect that it would require this much work. Honestly, at first I thought it would be much more straightforward. Um, I guess another see. Otherwise, I think well, I didn't expect to put that much work into it, but at the same time, I think so far it's been mostly straightforward. There are not like very deep theoretical questions that I've been stuck on. And the other um, small obstacle we've been facing is that there are some, it's a bit unclear what the requirements to enter the the verify-rust-std challenge are, and in particular because there are some licensing issues that currently my submission of Creusot to the repository is stuck on.
So you're not officially in the competition yet, even.
So that's right. I'm not yet officially in the competition.
Oh. Well, yeah, okay, I guess then that's good to know. What are the licensing issues? What license would you need to have?
The main issue is that we use the alter ego solver, which is has a non-free license, and on the verify-rust-std side, they have in their rubric they have a question about licensing, but and they just ask whether the licenses are compatible with the verify-rust-std project, but it's not clear what exactly the conditions for this compatibility are. And so we're just waiting for the Amazon lawyers to tell us what needs to be done about it.
All right. Well, good luck, I guess, then.
Thanks.
Yes. All right. And I think now is also a good time, I guess, then to thank our speaker again.
Thank you.
And also to end the session for today. I can unfortunately not yet announce anything for next month, but I guess stay tuned as usual. And with that, see you all around, and thanks again.